Thank you for the introduction. Okay, so like the title shows, I'll talk about fluid mixing in ideal systems and go on to some real system applications. So, so I'll begin with a broad overview of the fluid mixing process. So, mixing, as you all know, happens when two or more fluids combine to form a mixture. Now, there are many interesting processes which take place. Suppose there are mass, energy, and momentum exchange which takes place during mixing. And the most interesting thing is, so suppose when a blob of ink, as in the picture, mixes in a glass of water, so the large scales break down into smaller scales via intermediate length scales. So that is what is known as a cascade process. And so the cascade is a multi-scale process, and that's what makes the study of mixing quite interesting. Now, I have worked on mixing in driven systems, which are also called turbulent systems. Okay, so this is just to refresh your memory, refresh the idea of turbulence. So suppose we have the Navier-Stokes equation, and the nonlinear term here is called the inertia term, which is responsible for this cascade process during mixing or any kind of fluid flows. So the large structures get broken down into smaller structures through a series of length scales. And so this is a highly nonlinear or multi-scale process. Now, what are the approaches to study turbulence or fluid mixing in general? So there are several depending on the scales we are looking at. So in the large, so there is DNS, the direct numerical simulations, where all scales are resolved. And then in the other extreme, we have turbulence models here, where all the processes are modeled. And in between, we have large AD simulations, where some scales are resolved, but the rest of the process are modeled. So I have worked on direct numerical simulations, but today I'm going to talk about analytical models of turbulence, that is turbulence models, and how to use some of those concepts in ocean models. So like I said, I'll just first talk about some ideal systems. So by ideal systems, I mean very small scale systems, maybe of the order of meter scale, and where we just concentrate on the physics of the flow and nothing more computational. And then I will show how fluid mixing is studied in ocean models, where you really have to think about how the gridding, the meshing is done, and all that sort of stuff. Okay. In ideal the study of miscible fluids, that is when two fluids do not have these two fluids, just molecular. Two fluids. The kinetic energy starts increasing, and at some time, where the mixing is kind of maximum, there are filaments, many filamentous structures where the two fluids have completely mixed with one another. So this is a state when the kinetic energy is maximum, and the bigger blobs have all broken down into smaller sectors through a scalar procedure. And after this stage, viscosity sets in, and we have decay. So, took about 8 months in 1,000 CPU cores, including so the question, so these are the equations of the DNS that was solved. So it's a variable density flow, so density is not constant, and there is a weak compressibility condition, which looks like this. So these equations, when solved in the DNS, took about 8 months in 1,000 cores. So the question, yeah. Yeah. So the question is, can we build an efficient model for two-fluid mixing, which perhaps takes much lesser time, but we can capture the essential properties of the flow. For example, the evolution of kinetic energy or the Reynolds stress, which is like a velocity-velocity correlation, instead of the full velocity field. So to do that, we needed to build a turbulence model, and the properties of the model requirements were that the model should be multiscale in nature. That is, it should naturally capture the evolution of the scales. This is because the Navier-Stokes is inherently a multiscale system. So any model based on Navier-Stokes should capture the natural evolution of scales. Now, the model that we built or we studied for this is a Turbulent model. So two models are models which are functions of two different points in space. That is, the scale separation. And because of the scale separation, so in turbulence modeling term, it's also called a second moment closure model. So if we close the second moments, then we do not need ad hoc equations for closing the Navier-Stokes, closing the nonlinear terms. So basically, and it captures the evolution of brain scales naturally in the system. And the good thing about this second moment closure model is that this model can also capture strong transients. For example, when the fluid starts from a quiescent state and goes to a turbulent state, the model can capture this full evolution. And also the good thing is that this model takes just 2 minutes instead of the full DNS 8 months. Okay, so I will talk about how we obtain that time efficiency. So these are the variables that were used in the model. So first, there is the Reynolds stress tensor, which is like a correlation of velocity-velocity correlation weighted with the density. And then we have a turbulent mass flux velocity, which is similar, analogous to a momentum. And then we have a mixed parameter, which is a correlation of density and specific volume. So this mixed parameter denotes the stage of mixing in the model. So this is analogous to the mass of the system. So energy, momentum, and mass, possibly. Now, so how do we achieve that speed up in time? We did a reduction of problem dimensions. So basically, we reduced a 3D system to a 1D system. And that's how we achieved the speed up. So basically, all the variables, all the observables were expressed in terms of a center of mass and separation coordinate. And then what we did was we angularly averaged all these variables in K space. Now, this angular averaging was done assuming that there is isotropy in the system. And because of this angular averaging, we reduced a 3D system to a perfectly 1D system. And we can do this angular averaging because the system is isotropic and homogeneous.
Is that true of your initial condition also?
Yes. So that is a good question. So it was initialized such that it is homogeneous and isotropic. Only the scales were large, but yes, it was true. Okay. Yes.
That third moment in total for the second moment?
Yeah. Yes, that's right. Yeah, so I'll go to that. Yes, I'll go to that. Yes. So the gravity effect is kind of weak. So it is not. If you think like that, it is not. But in the scales we are looking at, that's just the body force, and we are just looking at the scale, how the scales evolve. So the system is such that it is maintained, the isotropy is maintained basically in the fully turbulent stage. Okay, so the system is homogeneous, and that's why we can drop off this center of mass coordinate because it is translationally invariant. Okay, so this is how we close the third order moments. We use the leaf diffusion approximation. So I'll go to what that is. So in that, so we assume that any dynamical variable can be written as a source term, a flux term, and the dissipation term. Now, this flux term is the Navier-Stokes third order moment, which needs to be closed. So the leaf diffusion approximation states that the flux, so the model is built in spectral space, by the way. It's all written in spectral space, in K space. So the equations are all Fourier transformed, and we build the model in K space. Okay. And in K space, approximation, which states that the nonlinear term can be expressed as an advection and diffusion term in K space. So there is an advection and diffusion term, and there is a turbulent time scale associated with it, which depends on the energy of the flow. And the claim is that when written like this, that is as a sum of an advection and diffusion term, the model the natural distribution of energy, momentum, and mass in the system. So this is okay. So yes. So this is the mass flux velocity. So there are three directions, as you know, X, AY. So AY is, I think I just wrote the Y for some reason. It's a misprint, but it's actually an averaged mass flux. It's an angularly averaged momentum. The homogeneity, I guess you are meaning that the isotropy is broken because of gravity. Yes. So we are in the regime, so there is gravity, and the viscous forces are competing with it, and there is a cascade of length scale. So we are concentrating just on the cascade. We are not looking at the large scale flows. So we are just isolating the physics of the cascade process. So yes, so this dp dy, there is a pressure gradient, of course, there is a drive, which maintains turbulence, but in those length scales, we are assuming that it is isotropic. Yeah. Okay. Definition of the parameter B, it's a correlation of specific volume and density. It's a correlation of density and specific volume. Yes. So basically, if you write down the density equation, there is the mass conservation from the density conservation equation, and then you correlate it with the specific volume equation. So then you obtain all these terms. And so here the gravity gives the pressure gradient, but it is only to maintain the turbulence. And we are not looking in a regime where it makes the fluid anisotropic. Yeah.
So sorry, you're
Yes.
saying,
Yes, sure.
you're saying that even after isotropically averaging,
Yes.
the pressure gradient term enters as a kind of source, a scalar source.
Right. Yeah. Yes. That's true. That's
So,
okay. Yes. This is the gravity is, it is there. It's constant energy input. Yeah. So, by the way, this gravity term, these are exact. These are not isotropic. I mean, these are exact terms as obtained from Navier-Stokes, but just isotropically averaged. And these are the model terms. The nonlinear term is the term that is modeled. All other terms are exact as obtained from Navier-Stokes. Yeah. Yeah. So that is basically, you can say it is by construction, because it follows from the works of Leith, that, yeah, the Leith model, right? Yes. So, of course, there are coefficients, and so all these coefficients you can basically calculate from the theories of single fluid turbulence, and assuming that a single fluid turbulence has the minus 5/3 energy spectrum scaling. And so all these coefficients can be derived theoretically, starting from the fact that the turbulence spectrum has a minus 5/3 scaling. So what we did in our work is we built the model and based on the Leith model, and then we compared our model. Yes. Sure. Okay. Yes, that is a good question. So, so there is a relation between the advection and diffusion. Yes. If you write down the equation, the constraint of the minus 5/3 scaling, and you calculate the different, and you just do a dimensional analysis kind of a thing, there is a constraint equation which comes up. So there is a relation between the advection and the diffusion term, like between the C's. What we found is the advection is twice the diffusion, like that. The magnitude of the coefficient is twice the diffusion. Yes. Oh, okay. I mean, I think so. Yes, there is a minus sign. So the magnitude of the coefficient is like that. Okay, so after that, what we were studying is how. So for this two fluid mixing problem, how does the time series compare with a fully resolved DNS? So that's what we saw, that the time scales were captured very well in the model. That is the time scales at which the momentum attained a peak. That is, this is the turbulent velocity attained a peak and decay, and even the energy peak was captured well. So the transition times were captured in this model, and there is some problem with the diffusion because the DNS really had a three-dimensional diffusion, and then errors, the numerical errors were different because it's a 3D code, but our model is just a 1D code. And so the diffusion area, the diffusion side is not captured very well for the energy. Okay. Right. So these were optimized, I did not show that. These were optimized using a Pearson's chi-square method to see if the curves were fitted, but all were within the all the values of the coefficients were around the values of the Kolmogorov exponent, that is -5/3 if we assume that the turbulent kinetic energy has a -5/3 scaling, then these coefficients have a particular value. And we saw that all these coefficients agreed to that. And we did it for different Atwood numbers, by the way. So here it's a very high Atwood number. So we also ran this for different Atwood number ranges, and the same set of coefficients agreed with all the models. So the model was general in the sense of Atwood number. That is, the coefficients did not vary as the Atwood number changed. Okay, so we can also predict spectra using this model because this is a 2-point model. So the spectra here. Okay. Yes.
You were imposing the full DNS spectrum also?
Right. Yes. Right. So the blue ones are the DNS, and the orange ones are for the model. So there are some step-like features because of the way the model. So the K grid in the model is defined as a logarithmic grid because there is in the spectrum of turbulence has a power law scaling. So the model is built on a logarithmic K grid, and so there are some step-like features, but this is just a numerical thing which gets diffused out in one time step. Yeah, so the orange is the model, and the blue is the solid green. There is quite good agreement between the two for a high Atwood number. Okay, so this is not so much related to anti-diffusion, but we were working on something which is, it's not a pattern formation, but you can stop the mixing at some length scale. So the things that I said so far, the two fluids mix down to molecular scales. So there is no length scale at which the mixing stops, but the mixing proceeds down to molecular scales. That is, they mix perfectly with one another. But we can stop the mixing at a certain length scale, provided there is a spectral block in the B equation. Because just setting the viscosity 0 won't stop the mixing because the cascade is there already. So we need to stop the cascade if we need to define a phase separation kind of a thing. So the turbulent time scale needs to be adjusted to give the formation of droplets and so on. So it is just that the spectra needs to be blocked at a certain length scale. And this again, it comes to phase separation and oil water separation and so on. But I won't show that much here because of time constraint. Okay, so yeah, so these were some areas where the mixed model was used. This was heavily used in an inertial confinement fusion of Los Alamos, where they had used a mixed model coupled with a DNS and so on, and also in some geophysical flows. So I'll switch gears a little bit to talk about geophysical flows and ocean modeling, that is. Sure. Right, exactly. Yeah. Yes, so that is an interesting question. There is some pile up observed in the B spectrum, that is when we ran the code. So there was some uh, backscattering involved. So for that, we need to adjust the parameters, the sizes of the outlets that we want and the experiments maybe to stop the pile up somehow. What needs to be taken care of? Right. So basically, the thing to look for here is that the B parameter should be conserved with time. The integrated B should be conserved with time to have a phase separated state. And that might give a system with no backscattering and less artifacts. Yes.
Then we're creating this way of introducing phase separation to instead actually starting with a energy functional for a composition variable which has phase separation, like nonlinear.
Right. Right. So that is a good question. So that will come in through the B equation, basically, but how to include the free energy functional, that is a question for now, because for now there is only the cascade. I mean, we are just modifying the advection and diffusion just to get this phase separation, but not doing anything to conserve. So this B field must be conserved. That is one thing. But yeah, this can be validated against the DNS simulations. Okay.
Yeah.
I mean,
Yeah.
yeah, it can be validated at some limit, but yes, yeah. Okay, so to talk about some ocean models. So oceans, why? So oceans has the largest heat capacity and so on, that we all know. So today I'm going to talk about how we incorporated tides in a climate model or general circulation model. So this real system and ocean model is kind of a way to show that how the approaches to mixing are widely different in between working with an ideal system where the number of forces are less and the boundaries are very well defined. But here, when we go to an ocean model, the boundaries are very complicated and we are looking at a spherical arc. And most importantly, there are multiple length scales. So mixing happens at different length scales. So how to take into account the multi-scale nature of ocean dynamics? So we did some basic preliminary work at Los Alamos. So I'm just going to talk about that. So we included, so why are tides important? So tides, of course, are important because of their interaction with eddies and tidal mixing and the response of tides to climate change as we have a sea level rise. And also in the interaction of tides with cryosphere is important. And the impact of tides on remote sensing missions, that is to remove tidal noise and so on. Now, most of these questions are actually addressable if we have a very high resolution simulation of a climate model with simultaneous tidal forcing and atmospheric forcing. So, so far, mostly the tides that were looked at, the tidal models were kind of 1D models. Those were separate from the ocean models. But what we did is we included the astronomical tidal forcing directly within the ocean model. Model that I will be talking about today is a part of the energy exascale Earth system model, which is an US Department of Energy model, and with most of the work done at Los Alamos. And particularly, I will be talking about impasse ocean today, which is an ocean model embedded within the energy exascale Earth system model. So, this model is known as model for prediction across scales, ocean. The salient feature of this model is it can capture the multi-resolution property in ocean dynamics. That is, it can capture eddies. I mean, it's an eddy resolving model. It can capture eddies and also the large-scale ocean circulations. So, and the way it can do it is the model equations are solved on an unstructured grid. So I will come to what an unstructured grid is. But unstructured grids are grids which can accommodate changing resolutions. So for example, in the open ocean, you need very less resolution, but in the coastal regions, you need higher resolution. So these changes in resolution can be very easily captured, I mean, very comfortably captured using the unstructured grids. Okay, so impasse ocean is traditionally a layered ocean model, 60 to 80 layers. But for our purposes, to lower the computational cost and to see more horizontal resolution, we ran it in a barotropic mode, that is a single layer mode. And we included tidal forcing, and we saw its effects on Antarctic ice shelf cavities. And these are benchmarked against the TPXO8 data, which is the satellite reanalysis data. Okay, so what are the general problems? So this is a very, I'll just give a broad overview of general problems with ocean models and so on. So in the spherical Earth, the latitude longitude grids, that is the spherical polar coordinates, were used. But there was a problem because there is a singularity at the poles. Because the grid spacing progressively went to 0 as we go to the poles. And this introduced a problem with numerical stability, because there is a CFL condition, and as delta x goes to 0, we have to reduce delta t also, and this created a stability issue with structured grids, that is with spherical polar grids. By the way, these are called structured grids because there is a coordinate line. There are defined coordinate lines, and also the grids can be identified with indices, that is I, J, K, and so on. So, so as you can see, as we go towards the poles, the grids become very distorted quadrilaterals, and the stability problem comes in. Now, so there have been many ways the problems are addressed. So I will just talk about the grids which are used to solve the polar singularity. So those are called semi-structured or unstructured grids. So for example, the cubed sphere framework is one of the ways the pole singularity is avoided, where you project a cube on a sphere, basically. So instead of a strong singularity at a pole, you have 4 weak singularities at the pole. So this is a semi-structured. Then you have tripolar grids where the singularities are moved over land and the ocean model can be run seamlessly. But of course, it is not general. Now, the thing that we did in this impasse ocean is the gridding using the Voronoi tessellations and icosahedral meshes. And so these are unstructured and no projection is necessary for Voronoi tessellation grids. So just to say that what are unstructured grids, so here the grids are placed in an irregular manner and there are no definite coordinate lines. And triangular elements are used to span the entire sphere. It is called triangulation. And the advantage is that the grids can be refined wherever necessary. So, okay, so we used a Voronoi tessellation approach in this impasse ocean, where we defined Voronoi regions over the entire sphere. And defining these Voronoi regions made our equations very easily solvable because we did not have to do any kind of projections. And then there was a regularization of this Voronoi grid into we can find the mesh density at a different location using this formula. Here the dx's are the grid spacing between 2 adjacent points and so on. So this gives a multi-resolution kind of approach. And so we worked with icosahedral meshes, which are initially we had. So icosahedral is a 20-phased structure, and by several bisections, we obtained a triangular structure spanning the entire globe. So the grids developed in this way. So this is from our impasse ocean simulation. So the important thing is that these are high quality meshes that obey all the conservation properties and stability criteria. And of course, the bisection of polygon faces continue to discretize into triangles because the triangles are important for unstructured meshes. And this is a finite volume method solved on an unstructured grid. So impasse ocean basically uses a finite volume method on an unstructured grid. And this very beautifully avoids the grid singularities at the 2 poles. Okay, so this is the Navier-Stokes equation that we used in our model. So it is written in a vorticity and kinetic energy formulation because it has to be solved on an unstructured mesh. But yeah, so there are Coriolis force and pressure gradients, and there are some drag schemes that we used, a topographic drag and a bathymetric drag. And then we have the conservation equations and the pressure equation.
So, yeah.
Right, okay, so that is, so wave drag basically happens when there is a shear between 2 layers of the ocean near the bottom, where So due to topography, due to the bottom topography, the water moves over uneven surfaces, and that creates many waves, internal waves. So because of interaction with the flow, and that creates a wave drag, basically. And we can, so there is a parameterized wave drag that we had used. It is linear in velocity. That's the assumption. Yeah. Yeah. On this one. Oh, so this is obtained from the nonlinear term. So you can write it, the nonlinear term in the Navier-Stokes. You can write it as a vorticity and kinetic energy formulation. K is kinetic energy, right? Yeah. Yeah. This is done because this model is solved on an unstructured grid, and there are some restrictions because the vertices are the vorticity is defined on the vertices and so on, and the velocities at the cell centers, I think, or the other way around. Yeah, sorry. Yeah. Right. So yes, so it's a tensor dependent on the topography. Yeah, on the topography. It is a tensor. Right. By hand. We have to, that's an input parameter. So yeah, that has the different scales of the topography also associated with it, the heights and so on. Okay, so tides, this is just, I think we all know that due to gravitational attraction between sun, moon, and earth, the tides are created. And our aim is to include the astronomical tidal forcing in this model and see how it behaves. So this is the tidal potential. It can be written as a series of sines and cosines, and where phi is the latitude, lambda is the longitude, and so on. So we study the effect of the dominant five tidal constituents, and see how it compares with TPXO8 results. Okay, so this is the eta is the sea surface height perturbation. So that is what is put inside the model. And some are semi-diurnal and diurnal components. So twice a day and once a day and so on. Okay, so this is our TPXO8 data that we obtained. I mean, this is the reanalysis of the satellite data. This has 1 by 24 degree resolution globally. And these lines are the tidal amplitudes and phases. So the lines denote the phase contours, and the colors are the tidal amplitudes in meters, actually. It is in meters. Yeah. Now, we compared this to our impasse ocean simulation, and yeah, so tidal phase and amplitude. So if we plot the difference plot between the TPXO8 and the impasse ocean, we see that there are some problem areas, as in a lot of errors happen at the Antarctic in the Southern Ocean, basically. So, and also the coast areas, but the coasts we are not resolving for now. So the Southern Ocean has a lot of errors, high errors. When we so this is in meters. Yes, right. This is in meters, right? So yes, and error, global average in centimeters that we got, the error, basically. Okay, so now also as we saw that this is near the Southern Ocean, which is dominated by Antarctic ice shelves. So we wanted to see if we could include the hydrodynamics due to ice shelves. So ice shelves are basically these very long, very ice structures that we see, and which apply a pressure on top of open ocean. So these are this apply this a very high pressure on the open ocean. So this is a schematic of the ice shelves, and you have the ocean here, the continental shelf here, and ice shelf jutting out, and it exerts the pressure. So what we did was, in our model, we accounted for that extra ice shelf pressure. And so this is how it was added, this extra ice shelf pressure. And we saw that these errors immediately improved when we added the ice shelf pressure. And just by accounting for extra ice shelf pressure, as a boundary condition to the whole model, the errors improved significantly. And there were many things that we have to study, the wave gaps, we have to optimize the wave gaps. And also we use the infrastructure and loading time, which I'm not talking about here, but we have done that. So this is 8 kilometers uniform global mean. So this okay, I see. Right. So there, so yes. So basically, including the ice shelf does something to the coastal regions also, but it could be so. Okay, so this is the difference. So I mean, this is just to show that ice shelves make the errors better. This is a polar south polar projection. So this is a so then we had some bar charts which show that the errors reduced drastically in the Southern Ocean due to the inclusion of ice shelves. So yeah, and so we had some tide gauge results as well. But yeah, the Southern Ocean tides are better when we include the ice shelf pressure just. So, and we did not include any ice shelf interaction. It was just the hydrodynamic pressure from ice shelves. Okay, yeah. So all these computers and so on, these are applications, and yeah, acknowledgements, and these are in reverse chronological order. So yeah. Okay, so thank you for having me here. Yeah.
Yes, question.
Yes. Okay. It's a parameter. Okay, it's right. So the two viscosity is constant, but there is a mass diffusion. Mm, so yeah, for the two fluids, the viscosity is constant, right? Yes.
But it's equal.
Equal, yes, so equal, sorry, yes. Right. So you can have a scale dependent viscosity here, which depends on scale, which depends on K. But at this level, we did not do that. Of course, it can depend on turbulence. Then it will change the time scales and so on. I mean, yeah, it can depend on scale, right? That is true. Yes. Okay. The limitations of, yeah, right.
Which method, part one or part two?
The part one,
Part one, okay.
yes. Of course, yeah. Yes, right. So these are, of course, this is for miscible fluids. You know, if you have strong surface tension between the fluids, this will not work. Yeah. Okay, I see. Uh-huh. Right. 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 So far from the boundaries, far from the so that there are no boundary effects. So we extended this model for an inhomogeneous system also. I did not show those results here, but it is done. So it is normally applicable for flows which are far away from boundary effects. And, scale, I think lane scales doesn't matter as much if you are in the turbulent regime, that is, if you cross a certain Reynolds number, I think it doesn't matter. It can be applied to ocean. The LEAT model is regularly applied in ocean model to see the energy cascades and so on. So it is done. So yeah, it can be applied to oceans or even laboratory flows like the ones I did here. So it's really that it should not be close to any boundary effects, and it should be as ideal as possible. Yeah, I mean, yeah. Yes, thank you.
Well, I have a remark. Can we go back to the beginning where you just said the variable density model?
Right.
I just want to next slide. There we are.
Yes.
The very small number of people in this room in February heard me give a talk on the variable density model, which is this. It's really Cook and Dimitakis.
Yes,
Variable density model for
yes.
wave mixing of two fluids. And I just wanted to point out that, as you've already said, that the problem is what it is compressible Navier-Stokes, that the model works out that you've got then a separate equation, third equation, div u is a Laplace, negative Laplacian of log rho. Okay, now if it was standard Navier-Stokes, incompressible, you could do that on a laptop, 1024 cubes on a laptop.
Right, yes.
But this one, because it's compressible, and you've got the div u condition, when you give across the main momentum equation, you've got a really horrible equation for pressure. And Libescu spent years working out how to do that.
Yes,
yes. It's incredibly expensive, as you say, it takes 8 months.
exactly. Yes, they use some, I think the Poisson solver to solve the pressure, yeah, on that. Okay.
Yes, it's incredibly expensive computation. But basically that is the variable density model, which, as you say, is just too expensive to do for a global,
Right,
for a global model.
right, yeah, it's extremely.
You had a question?
Yes.
So
Yes.
it's kind of a
Yes.
continuation of Sriram's question and your rejoinder to it. So,
Okay. Right. Right. So,
it wouldn't be a cutoff.
Right, the dynamics. Yeah, so as far as I am aware, at least these people did not do such elastic turbulence range. Yeah,
Not in the level of leaf model, but
not in level of
your
leaf.
DNS, you did it. Oh, sure.
Yeah.
More or
Yeah,
less,
with leaf model.
those in elastic turbulence induced by polymer.
So are you suggesting, are you suggesting like that you put in something like an Oldroyd beta into the lead model?
Well, that would be a simple way. I mean, has anyone done the leaf model before? The system would be a simple question.
Yeah. Yeah, so, right, yeah. Yeah, I think there were like Tim Clark and Bob Rubenstein were the people who were trying to do it, but then they went on to do other things. And
For that matter,
yeah,
leaf model.
okay.
You should know.
So this is supposed to drive the component.
Right.
So can I pull out from this an equation for the diffusion of the composite wave? I think so.
Right.
I don't see it. What I see is it differs from a ordinary one component incompressible fluid because the compressibility term is written in a way that has a Schmidt number or something.
Right. The Schmidt number, which is already.
You can answer that. You take two incompressible miscible fluids,
Right.
and you create them, you define a variable density for the mixture.
Sure. What I want to know is from this, can I discover the diffusivity for the relative density variable? If I wanted to write it in terms of a composite variable,
Right.
that should have
I
diffusion.
think, yeah, so,
I mean,
yeah,
I
so
said,
Lewis was
I'm sure either
explaining for plasma. Let me just see once. Yeah, I think I had it. 1 second. No, so yeah, so no, I don't think I have it here, but they were doing it for plasma. They were extending it and there they had it. I think just give me a moment. So there was one work which they did for different compositions. Yeah, going to field if, yeah.
Because the two components go diffuse volume component of different mass density.
Yes.
Right. Right,
We
there
have
was a,
That's the thing you've done that, I know.
okay,
So this is the permissible carbon.
Right, right.
It's normally,
Right. You take it above, you can take it above the, you know, above the separation.
I see, okay. So this is I mean, this was extended later as a
Right.
function of components, but it was more when it became a plasma sort of.
So, yeah,
I mean,
I can work on
sorry.
my anxiety for this purpose.
Okay, okay, sorry.
that,
Thank you for having me here.